So in this video, we will be tackling the situation given there are two blocks of mass M1 and M2 connected by a light inextensible string, okay, that passes over a frictionless light and frictionless pulley. Okay, the incline is also frictionless, and our goal is to calculate the acceleration of the blocks and also the tension in the string. We're just going to assume that M1 is going to go down and M2 is going to go up. If the opposite happens, it really doesn't change much in the problem, as you'll see. Okay, and then when we finish the problem, we'll also kind of figure out a condition for which, the condition between the blocks or the masses such that the system will remain in equilibrium. Okay, so that'll be at the very end of the problem. So what I would like you to do right now is draw the free body diagram for M1, draw it for M2. Do not do anything other than drawing forces on the free body diagram. Then, once you have the free body diagram, draw a separate picture, okay, with the two diagrams again, but this time break whatever you need to break into components, add whatever dotted arrows you need to draw, okay, and then take it from there. So let's pause, okay, do these two things, and then come back and let us check if your work matches with mine. All right, so I'm assuming that you paused, and I'm gonna just break the screen into two halves here, and first half will be my free body diagram. So I'm gonna draw it for M1. So the forces for on M1 are going to be M1G pointing down, and then it's going to be T pointing up. For the block on the incline, we have M2G pointing down, T pointing up, and we have Fn pointing perpendicular to the surface. Okay, so when you draw these, try to draw it neatly so that even if it's not perfectly perpendicular, it looks perpendicular. Okay, all right, so this should be your free body diagram. Nothing else should be on your free body diagram. No dotted arrows, no components, nothing. Okay, now having said that, now let's draw another set of diagrams that will help us write equations. Okay, and here we have M1. So for M1, we said earlier we have M1G pointing down, we have T pointing up, and since we assumed in the problem that M1 is going to go down, we can write M1A pointing down. Okay, now for the block on the incline, we have to be careful, like we already know. Okay, so we have M2. So let's look at all the forces on M2. We have M2G here, we have T here, and then we have Fn here. Okay, now we know that there is one force here that does not coincide with our axis. Again, what axis do we choose? We're going to choose an axis parallel with the incline and perpendicular with the incline. Okay, and the reason we choose this axis is because the block is accelerating in basically it's accelerating up or down the incline. So that's why we choose this axis. Now, having chosen the axis, we recognize that the only force we need to break into components, okay, will be mg. Now, if you remember from the previous video, we know that the angle that m2g makes with the y-axis is theta, and therefore the component perpendicular to the incline is going to be m2g cosine theta. Okay, the other component is going to be m2g sine theta. Okay, so at this point we have the component, all the forces for m2 that are along the x or the y-axis. Now I will also draw my dotted arrow, and I'm going to draw it pointing up the incline. I will put m2a on this arrow. Okay, now if you have all this in your picture, go ahead, write your equations, and then we'll come back. So pause, write your equations, and we'll be back. Alright, so I'm assuming that you did that. So I'm going to write our equations. For the hanging block, our equations are going to be m1g minus t is equal to m1a. Okay, now for the block on the incline, we recognize that Fn is equal to m2g cosine theta. However, because everything is frictionless, those two forces essentially cancel each other out, and nothing else happens. Later on, when we have friction, the Fn, okay, the contact force or the normal force will become an important part of our story, but that's not yet. So along the direction of motion, we have T pulling things up, and we have minus m2g sine theta, since m2g sine theta is pulling everything down, and this is equal to m2 times a. Okay, so I hope you understand this. Again, the benefit of writing the equations one below the other is you see right away that there's a negative t in one equation, positive t in the other, and we can simply add up these two equations. And when we do that, we get m1g minus m2g sine theta is equal to m1a plus m2a. If we take g if we factor g out from the left side, a from the right side, we would end up with an equation a equals m1 minus m2 sine theta, okay, times g all over m1 plus m2. Now, if you remember the Atwood's machine problem, okay, in that the theta would end up being 90 degrees, and if the theta is 90 degrees, then we would have sine theta to be equal to 1, and the answer for A would coincide with the answer for the Atwood's machine, okay. Uh, at this point, I expect you to be able to just find the tension, just plug it into one of the equations, and go ahead and calculate the tension. Okay, so this concludes this problem, and in the next video we'll take a look at a similar situation with multiple blocks attached to each other, and that should be the last in this series of problems.